Good morning, good afternoon, good evening, whenever you happen to be watching this video, and welcome to ENGR 231, Lecture 3, Part 1. In this part of the lecture, we're going to be looking at applying vectors to forces in 2D systems. So I'm going to look at, in the previous lecture, we looked at vector systems, adding vectors, both rectangular, polar, etc. And most of the time from here on out, we're going to be working with Cartesian vectors. And I want to first, in this portion of the lecture, in part 1 here, I want to look at how to apply 2D vectors to simple force systems. So, force vectors. And we're going to start with a very simple case, the 2D ones, which will be basically identical to the previous vectors we've been working with. And let's see here. So a force vector, of course, is simply a vector showing a force along a certain line of action. Has two major components. One will be its magnitude. Of course, its size in pounds, newtons, etc. Or any other convenient unit of force, or any other force unit you're using. And two, its direction. And that can be indicated either in polar form, rectangular form, etc. By angles or whatever method you're using. And the direction, we refer to this as the line of action. So, let us see how to apply force vectors to static equilibrium. That's what I really want to look at today, and in particular in this video for 2D systems. So, let's consider this. So, examples of force vectors. If I have a rigid body, for example, if I apply force to it, there will be, that force, maybe 10 newtons or something, it will have a magnitude and a certain direction. And I could model that as having, or describe that as having some angle theta, etc. Although, that's really not, this here is really not what we're going to be looking at today. We're going to be looking really at the point particle model. So, what we're going to be looking at is objects that we can approximate as point particles. So if I have an object that, again, we can treat all of the mass as if it's at its center, or if we can slice out a single particle in an object and analyze equilibrium there, then we can treat it as a point particle. So there may be a variety of forces acting on this in a single plane. But if this is going to be in equilibrium, all of these forces must have a vector sum equal to 0. So an F1, F2, F3, etc. So the conditions for equilibrium, for 2D equilibrium point particles, 2D point particle equilibrium, will be as follows. Because we're looking at point particles, we're only going to have to worry about translational forces, not moments. And because it's 2D, we're only going to be concerned with the x and the y axis. So the first equation that we'll be applying is the sum of forces equals mass times acceleration. However, we know that the acceleration is 0 because, again, this is statics class. So the sum of forces in the x direction is going to be equal to 0, and the summation of forces in the y direction is equal to 0. And this is fairly intuitive. You've probably seen this stuff before, or something similar to this before in physics courses. But what's really neat about this, or what's really maybe not so obvious about this, is that these represent equations. Well, obviously they represent equations, but these represent tools to solve for unknown quantities in a system. Basically, in a 2D point particle system, we have two equations, and we can solve for two unknowns. And those unknowns could be things like forces, they could be things like directions, they could be any number of things. But if we're looking at the equilibrium of just a single point particle, we'll never be able to solve for more than two unknowns. So let us look at a few examples of this and where we might apply something like this. So let's consider something, let's work through a problem. Let's start with a very classic simple problem. A basic three-rope problem. So let us say I have a set of ropes, like so, and they meet at a single point here, here, and then from this hangs a weight. And let's say this weight has this weight is, 10 pounds. And then let me go ahead and indicate some dimensions on here. Let's say this is at an angle of 30 degrees, and this is at an angle of 45 degrees. So the first thing I want to do, or actually all this is given, I should say, and then I gotta tell us what we're looking for. Given, and find the force in the three ropes. Now, at first you might think, oh, I have three ropes. Didn't I just say we could only solve for two unknowns? Well, that is two unknowns when you're looking at a single point. So the first thing I could do very quickly is get the tension in the bottom rope. That's going to be fairly easy to solve. And I will do a equilibrium on the weight itself. So I'm first going to do a 2D equilibrium on the weight itself, although we're only going to have one dimension to worry about because there's only forces in one direction, the vertical direction, on the weight here. So I have 10 pounds here, and then a force upward that I'll just call T1. T1. So then let's go ahead and solve or apply equilibrium. So I know the sum of forces in the y direction is equal to 0, and that will be T1 minus 10 pounds is equal to 0. T1 minus 10 pounds is equal to 0. And I can solve for T1 very easily and get, that's not 10, there we go, 10 pounds. I can easily find that T1 is equal to 10 pounds, no great mystery or surprise there. Now, let us next look at a second point particle. Now, what I'm going to do is, I am essentially going to cut out the bit of rope, the bit of matter that is right at the intersection of these three ropes. So I'm going to take that dot, that little bit of matter that's right at the intersection of those, and isolate that and say, okay, what kind of forces must be applied to that to hold it in equilibrium? So I have the T1, which I already calculated, as being equal to 10 pounds. And then I'll just say I have T3, or maybe T2 up here, at an angle of 45 degrees, and T3 at an angle of 30 degrees. Not F3, T3. T3 standing for tension. And now I want to apply equilibrium to solve for T2 and T3. So let's just go ahead and work through that. Sum of forces in the x direction. I will have negative T2 times the cosine of 45 degrees, that is the horizontal component of T2, plus T3 times the sine, or cosine of 30 degrees. Times the cosine of 30 degrees, and this comes to 0, so I have two equations, two unknowns here, or one equation with two unknowns, so I can't solve directly for anything with this, but I can simplify it at least. So let me just go ahead and simplify this at least, and I'll just maybe solve this for, T2 for example, or maybe T3 would be a little easier. T3 is going to equal T2 times the cosine of 45 degrees divided by the cosine of 30 degrees. Now let's go ahead and do this as an ugly decimal. Just collapse all of this down into a single number. So again, I would get that by adding T2 cosine 45 over to this side and dividing by the cosine of 30. So the cosine of 45 divided by the cosine of 30, this comes to a single ratio or single decimal of 0.816. So that is T3 then is equal to 0.816 times T2, or 81.6 T2's value. So T2 must be larger. Then I can do a sum of forces in the y direction, and I will have t2 times the sine of 45 degrees, although it will be the same as the cosine, of course, plus t3 times the sine of 30 degrees, and then I'll have minus 10 pounds, the t1, and that equals 0. Okay, so let me just go ahead and move this to the next slide. So I'm going to go back and forth a little bit here. So t2 sine of 45 degrees plus t3 sine of 30 minus 10 pounds is equal to 10, or sorry, is equal to 0. And I also have the result of my previous equation, which is t3 equals 0.816 t2. So I'm just going to go ahead and substitute this expression in for t3. So I will have t2 times the sine of 45 degrees plus 0.816 t2 times the sine of 30 degrees equals 10 pounds. So I'm going to factor out a t2, and I get that this, then I'll have t2 times the quantity, sine of 45 degrees plus 0.816 times the sine of 30 degrees. And this will, of course, equal the same 10 pounds. So I'm going to take all of this, everything in this expression, the sine 45 plus 0.816 times sine 30, and just get a single ugly number. So sine 45 plus the 0.816 times the sine of 30. And I get that 1.115 times t2 is equal to 10 pounds. And this t2 is equal to, and this t2, 10 divided by that, t2 is equal to 8.966 pounds. 966 pounds. And in turn, I can calculate t3. T3 is equal to 8.16 times t2, or 0.816 times 8.966. And so I can then just multiply that out really quickly. And I get that this is equal to 7.321 pounds. So I now have all of my tensions. T1 is equal to 10 pounds. T2 is equal to 8.966 pounds. And T3 is equal to 7.321 pounds. So a very simple, straightforward application of 2D point particle equilibrium. Solving for effectively, well, on one particle I'm solving for just just two unknowns, and that's what I can do with solving for just one particle. You can, and this also illustrates that we can solve for more than two unknowns, but we need more than one possible object to sum on. So anyway, let's look at some other examples. Maybe another example where I could show how we can solve for not just a unknown force, but perhaps an unknown direction. So let's look at this for a second. Let's say I have let's say I have something similar. Let's say I have a ring, and from this hangs a rope with a 50 Newton weight on the end of this. So 50 Newton weight. And attached to this, I have a rope that will only ever be able to carry, let's say this is a 30 Newton rope. What I mean by that is it is a rope that will only ever be able to carry 30 newtons. If I try to make it carry any more than 30 newtons, it's going to snap. And it's also being kept at, let's do this at an angle. Let's maybe put this at instead of giving the angles, let's do a slope relationship. Let's say this is a 3, 4, 5 triangle. Just for fun. For relative forms of fun. And let's see, let me play with some numbers here. That'll work. And then, so that's hanging from here. And then, let's say that I have a third rope that I'm asking us to figure out where we need to put it. So in other words, we don't know the theta, and I want to figure out where I should place this rope in order to get the desired, well, actually let me first do a quick calculation on this. I need to do a quick calculation to determine if this is even possible. Yeah, there's no reason this shouldn't be possible. That should be fine. Okay. The problem with laying things out with known forces and a known direction like that, or a known fixed force, if you're not careful, you'll make a problem that can't be solved, and it'll have no solution. But we'll be fine here. So let's just say this is an unknown force or a chord that will have a unknown force in it. So basically, I have two ropes here that are supporting the third rope and the weight, but for whatever reason, this rope has a breaking strength of 30 newtons, and I know the length of this, and I'm basically asking, okay, what angle do I have to hang this third rope in order to make this thing be in static equilibrium? So let me just go ahead and say this is given. And maybe I'll just write this out for brevity's sake. Find, 1, the angle that the third rope needs to be hung at for the system to be in equilibrium. Must be placed to keep ring in equilibrium. In equilibrium. And 2, the force that would be present in that rope. Maybe I can go ahead and draw it as a proper rope going to the ceiling. 2, the magnitude of force in the third rope. In the third rope. Now, the difficulty of this is that I want to assume that this has a force of exactly 30 newtons, so I really shouldn't say it has a breaking strength of 30 newtons. It would almost be like an impossible rope where, like, it is only stable for some crazy reason if it has exactly or pretty close to 30 newtons of force in it. So I suppose if we were particularly clever, we might actually be able to design by some clever mechanical linkages some ridiculous rope that it can only hold 30 newtons, no more and no less. And if you try to pull on it with less than 30 newtons, maybe it'll come apart somehow. And if you try to pull on it with more than 30 newtons, it'll come apart somewhere. Well, I guess if we didn't want to think of a clever mechanical linkage, for some crazy reason, I guess we could just literally have a force gauge in there. We could literally just have a force gauge and some sort of computer chip in there connected to a motor or something that if the force in there wasn't around 30 newtons, it would manually disconnect the rope for some crazy reason. I don't know why you would build such a thing. I have no idea why you would. But I suppose if you really wanted to, you could actually build a rope that would hold, again, via some sort of almost computer-controlled or actually computer-controlled linkage, you could actually build a rope that would hold only a desired amount of force. Although, again, I have no idea why you would do so. Although there might actually be some application for that I'm not aware of. Okay, so let's go ahead and do that, and we're going to start by doing a Freebody diagram. So let's look at this. Now let's go ahead and do a Freebody diagram. I'm going to neglect, I'm going to neglect drawing the Freebody diagram of this and say, okay, well, we've already looked at this kind of thing before. We know that it's going to have a downward force of 50 newtons. So we know the tension in this rope is going to be 50 newtons. So I don't really feel the need to go through all that again. I'll just say there is a 50 Newton force downward. And there is a 30 Newton force here at a 345 angle. Now, on this, I am going to also illustrate, let me not get ahead of myself here, let me just call this T for now, a tension T at some unknown angle theta. At some unknown angle theta. Now, what I might like to do is, on this, I am going to use this to illustrate how you can do something with, when you have slopes like this, usually I don't actually go, or when I have slopes like this, a system of slopes, I usually don't actually go and find the sign. If you already have in case you're not familiar with this is oftentimes statics is the first time students see this method. If you already have your slopes of your force, if you already know the direction of it and you know it via slopes, you don't need to actually go and calculate the angle. In fact, that makes it unnecessarily complex and just introduces more chance for error. See, think about this. If I have this, if I want to find, if I'm looking at this triangle, and here's the theta, and it's a 3, 4, 5 triangle. Now, I could get the x component by multiplying by the cosine of theta. And, however, again, if I wanted the x component of the 30 newtons, I could multiply 30 newtons by the cosine of whatever the theta is. However, go back to your trigonometry. Cosine of theta is just adjacent over hypotenuse, and that's 3/5. So I could do the inverse cosine and put the inverse cosine of 3/5, but I'm just going to take the cosine of theta and multiply it by 30. So if I want 30 cosine of theta, why don't I just multiply by 30 times 3 over 5? Because otherwise, if I do the theta, I'm basically taking the inverse cosine just to take the cosine again, or I'm taking the inverse tangent just to take the cosine of that angle. It just doesn't make sense. It's an extra step. It's just another source of potential error. It's just not worth doing. So when I have systems that I already know the slopes of, there is zero purpose to actually go and find those thetas. I just stick with the known slope ratios. So what I do then, or let's go ahead and apply this, I'll say the sum of forces in the x direction is equal to negative 30 newtons times, not the cosine of theta, but times 3 over 5. And then plus t times the cosine of theta, and this is then equal to 0. So in other words, t cosine theta is equal to, that's going to be, let's see, 30 divided by 5 is 6 times 3 is 18. 18 newtons. So t cosine theta is 18 newtons. Then, summation of forces in the y direction will be 30 newtons times 4 over 5 plus t, close the bracket, or parentheses, times c, or plus t times the sine of theta. And then this is not equal to 0, but minus 50 equals 0. Minus 50 newtons equal to 0. And so then I can say that t sine theta is equal to 50 newtons minus 30 newtons times 4/5. And 30 divided by 5 is going to be 6 times 4 is 24. So that is, and then so this is 50 minus 24, or 26 newtons. Let me go ahead and check that. So that's, yes, the 6, and then multiply by 4 is 24, and then, yep, 26 newtons. So I know that t sine theta is 26 newtons. And I'm going to try to squeeze this on one slide. So now I have two functions, or two equations, each with two unknowns, but thankfully this one isn't that difficult to solve. What I can actually do is I'm just going to go ahead and divide the equations by each other. T sine theta equals 26 newtons divided by t cosine theta and divided by 18 newtons. If you're having trouble remembering this kind of algebra, well, again, I know that this equation is 18. Whatever t cosine theta is, it's equal to 18. So if I divide the right side of this equation by 18, I can just divide the left side of the equation by t cosine theta, because that way I'm just dividing by 18 on both sides. And the real trick of this is that the t will cancel out. And also, I can say that sine of theta over cosine of theta is just tan theta. So tan theta then is equal to 26 over 18. 26 divided by 18. And if I take the inverse tangent of 26 over 18, that will then come to, and this will not be a nice even number like the other ones. Let's say 26, I'm zooming ahead, 26 divided by 18, and that will be 55.30 degrees. And then if I look here, I can see that t is going to be equal to 18 divided by the cosine of 55.30 degrees, and I'm sorry, no, I'm squeezing this in here. The cosine of 55.3 degrees, 3 degrees, and that comes to 18 divided by that, 31.62 newtons. 31.62 newtons. So we have the angle and we have the force in the cable. We have succeeded in solving for this, in solving for all the desired quantities. Now, finally, the last thing I'd like to look at in 2D point-particle equilibrium is how we can have a system that becomes unsolvable. What happens if you do a system like this and you try to solve for more than two unknowns on a single point particle? So let's say we have something like this. Let's say I just tell us that there are maybe something like this. Consider a point particle has forces A and B applied. Or actually, maybe first I will indicate why the opposite, where you have a system where there are not enough flexibility in order to actually arrive at a solution. So this would probably be a true no solution problem. Let's say I go and set up a system where I tell us that there is a 10 Newton force at an angle of 30 degrees, and there is a 20 Newton force, oh, not 20 degree force, 20 Newton force at an unknown theta. And I tell us find theta. So we're told that we have 10 newtons at an angle of 30 degrees above the negative x-axis and 20 newtons at some unknown theta. And I'm also told this system is in static equilibrium. Static equilibrium, solve for theta. So there again, there is a point object at the center. Solve for equilibrium. Or sorry, solve for the unknown theta. So let's try this. And so let's go ahead and do a sum of forces in the x direction. I will have negative 10 times the cosine of 30 degrees plus 20 times the cosine of theta, oh, not co-theta, cosine theta, is equal to 0. So cosine theta is equal to 10 sine 30 divided by 20, or that will come to sine 30 divided by 2, or just 0.25. And so then theta is equal to the inverse cosine of 0.25, and that comes to 75.52 degrees. So doesn't sound that bad so far, sounds pretty reasonable. What's the problem? It seems like I have an answer. Well, look what happens if I try to do a sum of forces in the y direction. If I try to do a sum of forces in the y direction, what I will find is the following. So I'll have 10 newtons times the sine of 30 degrees. Oh wow, I screwed that up big time, didn't I? Sorry about that. Derp, to err is human. Cosine of 30 degrees and cosine of 30 degrees there. Sorry about that. So 10 cosine 30 divided by 20. Math errors, who needs them? Let's see, so that is actually 0.433. I meant this problem to be unsolvable, but not because of human error. And if we go ahead and do this, we'll get, if I take the inverse cosine of that, I will get 64.3 degrees. 64.34 degrees. Okay, now let's go ahead and do the sum of forces in the vertical direction. 10 sine of 30 degrees plus 20 sine of theta is equal to 0. So then I can get sine of theta is equal to negative 1/2 times the sine of 30 degrees, which will be negative 1/4. Negative 1/4. So let's put that there, times sine of 30, and negative 1/4 indeed. So then I can get theta is equal to the inverse sine of negative 1/4. And that then comes to, negative 14.48 degrees. That's not good. Well, good. It may seem like I've made some horrible mathematical error, but in fact, unless I have without my knowing it, this problem is, as I set it up, deliberately unsolvable. See, this is what I would call an over-constrained problem, or an over-constrained system. I essentially have too few unknowns. So in other words, in order to make this thing at equilibrium in the x direction, theta would have to be at 64.34 degrees. In order to be in equilibrium in the y direction, this would have to be down here at negative 14.48 degrees. And it's impossible for the rope to be at both places at once. It can't be at two places at once. So this thing cannot be in static equilibrium as described. This problem has no solution. This problem has no solution. There is no theta that I can put this thing at that will result in this being at static equilibrium. It is fundamentally impossible. Now, again, fundamentally impossible as long as I insist on both forces being at, well, this force being at 10 and this force being at 20. If I'm willing to accept some other force here, then it could certainly be in static equilibrium. Let's look at the opposite case. What if you have too many unknowns? What if you have too many unknowns? So let's say I have something like this. Let's look at something similar. And let's say I had, I don't know, 4 forces on an object. Or maybe 3 forces on an object again. We can still keep things relatively simple. But let's give us 3 unknowns. So I have one force of 10 newtons at an angle of 20 degrees. I have a force of 30 newtons at some unknown theta 1. And then I have some unknown tension at some unknown theta 2. So maybe I'll just call this T2 to be consistent. So if I go and try to solve this, let's go ahead and try to do this. Let's start with the summation of forces in the x direction. I will have negative 10 times the cosine of 20 degrees plus 30 times the cosine of theta 1, the cosine not 30 but theta 1, plus T2 times the cosine of theta 2 equals 0. And so I get that, let's see, 30 cosine theta 1 plus T2 times cosine theta 2. T2 times the cosine of theta 2 is equal to 10 times the cosine of 20. I'll go ahead and leave that as just an ugly decimal for now, or make that. And that would be 9.40, or 9.397. Newtons. And then summation of forces in the y direction. I would have 10 newtons times the sine of 20 degrees plus 30 newtons times the sine of theta 1. And then minus T2 times the sine of theta 2 equals 0. Okay. So I then have 30 newtons times sine theta 1 minus T2 sine theta 2 And I can go ahead and put that 10 sine of 20 on the other side. And that will come to 3.420. 3.420 on that side, 3.420 newtons. Oh boy, there doesn't really seem to be a good way of solving this, does there? So if I tried dividing these equations out by each other, well, that wouldn't work anymore. Basically, there is no way to solve these two equations. I could play around with these equations if I wanted to, but fundamentally, I still have three unknowns and two equations of equilibrium, or just two equations. I cannot solve for these. Solve mathematically. I cannot solve mathematically for three unknowns with two equations. It is simply not possible. Three unknowns via two equations. That is simply not possible. So this system has no unique solution. So I wouldn't say the system has no solution. Rather, this system has infinite solutions. There are an infinite set of possible answers to this particular problem. Again, we have too many unknowns, and there are an infinite number of arrangements that there is, or I could also say, you also see it suggested, there is no unique solution. So we could just go and pick a value for T2, and then we could easily calculate theta 1 and theta 2, or I could pick theta 1 and calculate what the corresponding theta 2 and T2 are, but there is no unique solution that just off of this problem alone, just by looking at this problem and working through what was given, we could find a final set of values for this. Alright, so hopefully that serves as a useful introduction to force vectors, at least exploring them for 2D systems. And in the next parts of the lecture, we'll be looking at 3D vectors, and in particular 3D force vectors, and some of their various issues and applications. Alright, that'll do it for now. Thank you for watching, and I'll see you soon in part 2. Thank you.